On Christmas morning 2021, a rocket carrying the James Webb Space Telescope cleared the launch pad and headed for a point 1.5 million kilometers from Earth. Its objective, to capture light that has traveled across the cosmos for over 13 billion years. Astronomers had clear expectations for what the early universe would look like. They believed the first galaxies would appear as small, dim, featureless blobs of gas that had only just begun to merge. But the data coming back from Webb showed something else. It revealed massive, structured spiral galaxies existing in an era where they shouldn't be possible. A mature galaxy appearing just a few 100 million years after the Big Bang creates a timeline paradox. It suggests that our current understanding of how matter clumped together in the early universe is missing a significant piece of the puzzle. This discovery appeared to directly contradict the standard cosmological framework known as the Lambda CDM model. This model is the result of a century of research. It provides the mathematical evidence for the Big Bang and explains how invisible dark matter and the expansion of dark energy shaped the universe we see today. As the Webb anomalies went viral, news headlines described a state of panic at the disks, with some suggesting that our entire history of the cosmos was about to be rewritten. The pressure was on to determine if the telescope had found a flaw in cosmology's foundations, or if we were simply misinterpreting the light it was seeing. To understand the standard model, we must look at the macro scale. After the Big Bang, tiny quantum ripples expanded into dense pockets. Dark matter pooled here, forming gravitational wells. This mass pulled in gas, weaving an interconnected network known as the cosmic web. The Lambda CDM model charts this structure with high precision. It accounts for an energy budget where 70% of the cosmos is dark energy and 30% is matter. But while these rules dictate the broad strokes of gravity and expansion, they are too generalized to predict the behavior of individual stars or the internal dynamics of a single galaxy. Local development is governed by a separate set of microphysics, these specific recipes that dictate how galaxies form. Unlike smooth dark matter, regular gas is turbulent and chaotic. It heats, cools, and compresses in ways difficult to model. A galaxy's visible size and brightness are determined by these messy variables, specifically how efficiently gas turns into stars and how those stars live and die. The macro equations of gravity cannot predict the exact intensity of light an individual gas cloud will emit. Scientists were comparing the messy micro-level light emissions seen by Webb against the rigid macro-level rules of gravity. This disconnect created the perfect environment for a scientific misinterpretation. As astronomers reviewed the Webb data, they looked for a different explanation. What if these early galaxies aren't actually as massive as they appear? This brings us to the stellar initial mass function, a calculation to determine the ratio of massive stars to small stars born within a galaxy. This chart shows the distribution of stars we see today. In the modern universe, there are vast numbers of small, faint stars and only a few massive, bright ones. Before Webb, it was assumed the early universe followed the same pattern. But conditions in the early universe were different. The pristine chemistry of that era allowed for the birth of exceptionally massive stars. When the bars on the chart reverse, the galaxy becomes flooded with intense light. Webb was seeing galaxies filled with these hyper-bright stars remain secure. It continues to be our most accurate map of the macro-universe's gravity and expansion. Webb's observations revealed that the early universe was more active and complex than we previously imagined, showing that star formation was occurring with an intensity that older models hadn't accounted for. Powerful new tools like the Webb telescope don't always destroy our scientific foundations. Frequently, they provide the essential new data required to refine the complicated, messy recipes that make up the universe.